What if one of the strangest visitors from deep space just turned out to be far more dangerous than we ever imagined? Michio Kaku has revealed new data about 3I Atlas, and the findings are sending shockwaves through the scientific world. At first, astronomers thought it was just another dying comet, nothing more than ice and dust drifting across the cosmos. But that assumption didn't last long. Atlas isn't following the rules. It's racing through our solar system at over 130,000 miles per hour, its path bending in ways that defy standard physics. Even stranger, its chemical signature doesn't match anything we've catalogued. Not from Earth, not from our solar system, not from any known comet or asteroid. To Kaku, this isn't just an anomaly, it's a warning. Could Atlas be evidence of processes we don't yet understand? Or is it something far more unsettling, something that may have been designed rather than formed by chance? Whatever the truth, this discovery is forcing scientists to rethink what really drifts between the stars, and whether we've just had our first brush with the unknown. On July 1, 2025, the Atlas telescope in Chile picked up a blip, just a faint streak against the background of the Milky Way. Within hours, data flagged it as something extraordinary. This wasn't another asteroid or a routine comet. The object's speed alone, over 137,000 miles per hour, meant it couldn't possibly belong to our solar system. Its path cut straight through, moving too fast for the sun's gravity to pull it back. The international network of observatories snapped into action. Within a day, astronomers from Hawaii to South Africa confirmed what the Atlas team suspected. This was only the third time in history that a visitor from another star system had been caught racing through our cosmic backyard. That 3I in its name. It stands for Third Interstellar. The first was Oumuamua in 2017. A cigar-shaped mystery that spun out of reach before anyone could get a good look. Next came Borisov in 2019, a comet that looked almost familiar until its chemistry upended expectations. Now, 3I Atlas. Bigger, faster, stranger. Each time, the odds of such a discovery seemed astronomical. Yet here it was, staring straight at us from the void. The Atlas team at the University of Hawaii, Larry Denyo, John Tonry, and their colleagues were the first to spot it. They watched as the object's trajectory was plotted, a hyperbolic arc unbound by the sun, set to slice through the solar system and back into interstellar space. The confirmation came fast. Within 24 hours, telescopes on 5 continents had locked onto its path. The data left no doubt. This object was not from here, not from anywhere nearby, and its course would bring it closer to our planetary neighborhood than any previous interstellar visitor. For a brief moment, the global astronomy community was united in a kind of stunned exhilaration. The discovery meant more than just another data point. It meant direct evidence, again, that our solar system is not isolated, that debris, comets, and perhaps even something more can cross the gulf between stars and pass through our midst. The Atlas team's alert triggered a race. Who could gather the most data before this cosmic stranger slipped away for good? In the middle of this scientific storm, one name kept surfacing in late-night emails and urgent interviews: Michio Kaku. Known for translating cosmic mysteries into plain language, Kaku began reviewing the data as soon as it landed in public archives. He wasn't alone. As news of 3I Atlas broke, astronomers, physicists, and planetary defense experts scrambled to understand what set this object apart. The stakes felt higher this time, not just because of its size or speed, but because of what early readings hinted at: a set of properties that didn't match any known comet or asteroid, here or elsewhere. Around the world, Research teams calibrated their telescopes, ready to capture every possible detail. The global response was immediate. The object's rarity, only 3 ever seen, meant every scrap of information could change what we know about the galaxy. For the next few weeks, the world's most powerful observatories would focus on a single fast-moving target. The clock was ticking, and every minute counted. But as the data poured in, it became clear. 3I Atlas wasn't just another cosmic rock. Its arrival would force scientists, and everyone watching, to rethink what's possible when something truly alien passes through our solar system. And the more they looked, the more the story began to spiral into the unknown. Nothing in our solar system moves like this. 3I Atlas is tearing through space at over 137,000 miles per hour, faster than any planet, asteroid, or comet ever recorded by human eyes. To put that in perspective, it's more than 55 times the speed of a bullet fired from an assault rifle. At this velocity, it would cross the distance from New York to Los Angeles in under 2 minutes. Even the fastest spacecraft ever launched by NASA, the Parker Solar Probe, crawls compared to this. Atlas would lap it as if it were standing still. This is not just a fast-moving rock. Astronomers classify its speed as hyperbolic excess velocity, meaning it's not just passing through, it's on a one-way trip. The Sun's gravity, which holds every planet and comet in its grip, can't even slow this object down. 3I Atlas is moving so quickly that nothing in our solar system could have launched it. It's an outsider, crossing the gulf between stars, immune to the rules that bind everything else we know. The numbers push the limits of imagination. At 137,000 miles per hour, Atlas covers nearly 38 miles every second. In the time it takes to blink, it's already moved farther than the entire width of Manhattan. There's no force on Earth, or in the solar system, that could have given it this kind of momentum. The only way to reach these speeds is to be flung out from another star system entirely, ejected by the chaos of planet formation or a catastrophic collision billions of years ago. Astronomers call this kind of path hyperbolic. It's the trajectory of a projectile that can never return. When they plot its course, the math says it's not just visiting, it's escaping forever. This is the same kind of orbit followed by Voyager 1 and 2, the spacecraft humanity sent to the edge of the solar system. But even those took decades and the most powerful rockets ever built to reach escape speed. 3I Atlas is moving more than twice as fast as Voyager, and it's been traveling for eons. The object's speed isn't just a curiosity, it's a warning. Anything moving this fast packs an unimaginable amount of kinetic energy. If 3I Atlas were to collide with a planet, the impact would release energy thousands of times greater than the largest nuclear weapon ever detonated. Fortunately, its course keeps it well clear of Earth. But the raw power behind that velocity is enough to make even seasoned astronomers uneasy. The faster scientists measured, the more questions surfaced. Where did it come from? And what could have launched it with such force? What kind of catastrophic event could propel a chunk of ice and rock to a speed that defies the Sun's gravity? The numbers alone hint at a violent past, something powerful enough to hurl a mountain-sized object out of its home system and send it wandering the galaxy. But speed is only the beginning. As telescopes tracked Atlas across the night sky, the data started to reveal something even stranger. The chemistry of this visitor didn't fit any known pattern, and that's when the story took a turn that no one expected. On August 25th, the James Webb Space Telescope delivered its very first full-spectrum reading of 3I Atlas. What astronomers found in the data wasn't just surprising. It was almost impossible to compare with any comet ever studied, whether inside our solar system or far beyond. The spectrum was ruled by a single molecule, carbon dioxide. Not a small trace, not a minor surplus. CO2 completely dominated the reading, drowning out water vapor at a ratio of 8:1. For comparison, most comets in our solar system release far more water than carbon dioxide as they warm near the sun. Even the rare outliers rarely exceed a 2:1 ratio. Yet in this case, water looked like nothing more than an afterthought. The sheer scale of this anomaly left planetary scientists scrambling for answers. Some proposed that the comet might have formed beyond what's called the CO2 ice line, a region in a young star's disk where temperatures are cold enough for carbon dioxide to freeze. But water ice forms even farther out, which made the idea less convincing. Others suggested that only intense radiation or some exotic process could strip away so much water, leaving CO2 behind as the main signature. Still, the numbers from JWST's August observation were undeniable. 129 kilograms of carbon dioxide erupting every second, compared to just 16 kilograms of water. That's an 8:1 CO2 to H2O ratio, by far the most extreme ever recorded for any comet. And this is more than just an odd chemical quirk. A ratio this skewed points to an origin in a dramatically different kind of environment, maybe in a system with a hotter, more massive star, or perhaps back in a time when the galaxy's chemistry was still shifting and evolving. Martin Cordner and his JWST team ran through every scenario their models could imagine. None of them worked. In our solar system, ice lines clearly determine where different ices can survive, while planets and comets form. But even the most radical models never predicted a comet this rich in carbon dioxide and so depleted in water. The implications stretch far beyond a single comet. If 3I Atlas truly formed in a region where CO2 ice was abundant and water scarce, it suggests that planetary systems across the galaxy could be far more varied than we've assumed. Or maybe this comet was transformed by cosmic rays or shaped by supernova explosions in the galaxy's thick disk, its chemistry rewritten over billions of years. Either way, the August 25th readings forced astronomers to rethink how and where comets like this can form. They also opened up a new mystery. If the ratios are this extreme, what other elements or compounds might also be missing or unexpectedly present in the next set of spectra? The answers could upend our current models of planetary chemistry and hint at processes we've never observed before. But the strangeness didn't stop there. On July 25th, the Very Large Telescope captured the first ultraviolet spectra of 3I Atlas, and the data sent another shockwave through the scientific community. Researchers expected to see the familiar signatures of vaporizing metals as the comet drew closer to the sun. Instead, the spectrum revealed something baffling: clear, unmistakable lines of atomic nickel, but no trace of iron. On Earth and across our solar system, nickel and iron are inseparable partners. They are forged side by side in the hearts of supernovae, discovered together in meteorites, and released together when comets heat up. But in this comet, only nickel was pouring off the surface. Iron, the single most common heavy element in the universe, was missing entirely. From mid-July into August, Rohan Rahat Gaonkar's team at the VLT tracked the nickel emission growing stronger and stronger. By the time 3I Atlas had closed in to 2.85 astronomical units from the Sun, it was shedding nearly 5 grams of nickel every second. The numbers looked similar to those measured in some solar system comets, except for the shocking absence of iron. The most trusted models of comet chemistry offered no explanation, In every comet ever studied, nickel and iron vaporized together, their emission lines rising and falling in perfect step. Yet here, the iron signal was completely flat. No hint of it at all. Speculation quickly spread. Some scientists suggested exotic chemistry might be at play. Perhaps nickel was trapped in unusual organometallic compounds like nickel tetracarbonyl, which break down at lower temperatures than the iron-rich minerals usually found in comets. Others wondered if cosmic rays, after billions of years drifting through interstellar space, had stripped away iron from the surface, leaving nickel behind. Yet no one had ever seen this pattern before. The data left astronomers with a stark possibility. 3I/Atlas had been shaped by processes completely unknown in our solar system. And the nickel puzzle wasn't the only strange clue. The timing was off too. Normally, cyanide gas is the first to appear as a comet nucleus warms. But in 3I/Atlas, nickel vapor showed up before cyanide ever appeared. That flipped the standard script for comet activity, hinting that this nucleus was either built from unfamiliar building blocks or altered long ago by violent ancient events. Each new spectrum added another layer to the mystery. Nickel with no iron, outgassing in the wrong order, chemistry that seemed to bend or even break the rules written by every comet observed so far. For the team at the Very Large Telescope, the lesson was obvious. The old rulebook no longer applied. The paradox of this comet's metal vapors wasn't just another puzzle. It was a signal that the galaxy holds chemical surprises far beyond what Earth's laboratories can create. As more data piled up, it became increasingly difficult to argue that 3I/Atlas was just another ordinary cosmic snowball. Its chemistry demanded a completely new way of thinking, and the search for explanations had only just begun. Meanwhile, outside the scientific community, the story took on a life of its own. Viral headlines exploded within hours of the first 3I/Atlas data release. Social media feeds overflowed with dramatic banners. Michio Kaku issues terrifying warning, and Kaku reveals 3I/Atlas secrets NASA won't admit. Click counts skyrocketed. Some videos racked up more than 10 million views in only a few days. But behind the spectacle, something didn't add up. The actual research teams, astronomers like Larry Dino and John Tonry, had never spoken to these channels. None of the so-called Kaku quotes appeared in press releases, interviews, or published papers. Instead, content farms pieced together old clips of Kaku discussing black holes or gravity, layered on AI-generated narration, and paired it with fresh telescope images of 3I/Atlas. The result was a self-feeding loop of hype, speculation, and manufactured authority, designed solely to keep people clicking, sharing, and commenting. As the viral wave grew, so did the credibility gap. On one side stood real-time science, astronomers posting raw spectra, refining orbital models, and openly debating the comet's bizarre chemistry. On the other side surged a flood of algorithm-driven content that blurred the boundary between scientific mystery and manufactured drama. Some videos even recycled scripts word for word, swapping out Oumuamua for 3I/Atlas and simply tweaking a few numbers. Engagement metrics became the new currency: likes, shares, and views, outpacing peer review and careful analysis. Michio Kaku's name turned into a kind of digital shorthand for cosmic authority, invoked whether or not he had ever commented. The more outrageous the headline, the faster it spread. Soon, fabricated claims about alien probes and existential threats were being attributed to him without a single source, citation, or shred of context. For viewers, sorting fact from fiction grew harder with every viral post. Even mainstream outlets struggled to keep up, sometimes echoing the hype just to stay relevant in search results. Meanwhile, serious researchers watched the spectacle unfold. Harvard's Avi Loeb, for example, had his own controversial takes on interstellar visitors, but at least his papers were public and his name attached to the arguments. With 3I/Atlas, the noise made it almost impossible for genuine scientific debate to break through. Instead of focusing on the real anomalies, the CO2 dominance, the missing iron, the object's wild speed, the conversation drifted toward whatever headline generated the most outrage or fear. This disconnect wasn't just an annoyance, it risked drowning out the real story. That 3I/Atlas was challenging everything astronomers thought they knew about how comets form, what gets ejected from other star systems, and even how old some of these visitors might be. But in the algorithm-driven scramble for attention, the hard work of data analysis and skeptical inquiry took a back seat. The result? A credibility gap wide enough to swallow the truth, and a reminder that in the age of viral science, expertise has to fight for every minute of attention it gets. Harvard astronomer Avi Loeb and his colleagues have run the numbers on 3I/Atlas's path through the solar system. What they found caught the attention of more than just comet watchers. According to their calculations, the odds of a random interstellar object passing this close to 3 major planets, Mars, Venus, and Jupiter, are staggeringly low, just 0.005%. That's 1 in 20,000. For context, 3I/Atlas will pass within 0.19 astronomical units of Mars on October 3, 2025. Less than 29 million kilometers. A month later, it crosses within 0.65 astronomical units of Venus. And by March 26th, it comes within 0.36 astronomical units of Jupiter. These aren't distant flybys. In cosmic terms, they're near misses, each one a rare encounter on its own. Together, they form a sequence that's almost never seen in the history of planetary astronomy. From an engineering perspective, this trajectory looks eerily familiar. When NASA plans missions like Voyager or New Horizons, mission designers calculate precise paths that use planetary gravity to slingshot spacecraft through the solar system, conserving fuel while maximizing speed. These gravity assists, sometimes called gravitational slingshots, are the most efficient way to visit multiple worlds in a single trip. For 3I/Atlas, the alignment is so precise that it could, in theory, drop in on Mars, swing past Venus, and then slingshot toward Jupiter, all without using any onboard propulsion. Loeb's team points out that if someone or something wanted to deploy observation devices across multiple planets, this is exactly the trajectory they'd choose. But the math is only part of the story. The timing is just as strange. 3I/Atlas will reach its closest approach to the Sun, while hidden behind it from Earth's view, making detailed observation impossible during the most critical phase of its journey. That window, when the comet is brightest and most active, coincides with a period when it can't be seen by any ground-based telescope. Statistically, the chance of all these factors lining up by accident is tiny. Loeb's analysis doesn't claim proof of intent, but it raises a question that's hard to ignore. Is this path just a cosmic fluke, or could it be the result of something more deliberate? Most astronomers remain cautious. They point out that while the odds are long, improbable events do happen when the universe is as vast and chaotic as ours. Still, the data is enough to keep the debate alive. The probability calculation, 0.005%, serves as a reminder that sometimes the universe throws a curveball that looks almost too perfect to be chance. Whether it's the result of natural chaos or something else, 3I/Atlas forces us to confront the possibility that the cosmos may hold patterns we don't yet understand. And as this interstellar visitor races past 3 planets in quick succession, the question lingers. Are we witnessing a rare accident of physics, or is there a deeper message written into its path? The scale of time that 3I/Atlas brings into view is nearly impossible to fully grasp. This traveler began its journey long before Earth had oceans or even an atmosphere, before the Sun itself had fully grown into its steady middle years. For billions of years, it wandered through the silent gulf between stars, unseen and untouched, carrying within it the chemical traces of a star system that disappeared long before our own ever began. The sheer numbers themselves are breathtaking. A path through the galaxy that may have started some 7 billion years ago, back when the Milky Way was still forming, when its thick disk was crowded with old, metal-poor stars. To stand here on Earth and watch such a visitor pass is to feel the full gravity of cosmic history. Everything we think of as permanent, mountains, rivers, cities, even the continents themselves, are only recent developments compared to the age of this lone shard of ice and stone. The atoms it holds have witnessed the birth and death of stars, the forging of heavy elements, and the slow swirl of gas and dust that would one day become suns and worlds. When seen against such deep time, human history shrinks into almost nothing. The span of a civilization, even the whole lifetime of our species, is just a brief spark in comparison to the long journey of 3I/Atlas. Yet within that thought lies something quietly exhilarating. For a few short months, tools built by human hands have traced the arc of an object older than every city, every language, every story ever told. The data streaming back from telescopes is more than just a record of chemistry and motion. It's a message from before memory itself, a direct connection to the galaxy's earliest years. Its path, its velocity, even its strange chemistry are written in a language older than biology, older than Earth itself. It's easy to feel small in the shadow of such immensity, but there is a profound wonder in knowing that, despite our brief existence, we've learned how to read these messages from the stars. The same species that once trembled at comets as omens now studies interstellar visitors with machines orbiting far above our skies. 3I/Atlas will soon slip back into the blackness, vanishing beyond reach. But the questions it leaves us, about origins, about time, about our place in the universe, will remain. The cosmos is vaster than measure, and our role within it may be fleeting. Yet for one brief moment, we have seen something ancient move across our skies. And in that moment, we have glimpsed both the enormity of the universe and the rare privilege of being able to wonder at it. When 3I/Atlas was first spotted on July 1st, 2020, FRMNIA-25, it became only the third confirmed interstellar object, racing through space at more than 137,000 miles per hour. Data from the James Webb Space Telescope revealed something astonishing: an 8:1 carbon dioxide to water ratio, wildly different from any comet seen within our solar system. Observations from the Very Large Telescope added another puzzle: nickel emissions with no matching iron, a pairing that current models cannot yet explain. Even after intense study, the origins of these chemical fingerprints remain unknown. Using Gaia star maps, astronomers traced its path back toward the Milky Way's thick disk, marking it as possibly older than the Sun itself. While some scientists, including Avi Loeb, stress the unlikeliness of its orbit, the broader consensus stops short of firm conclusions. As Michio Kaku pointed out, 3I/Atlas forces us to recognize just how much of our cosmic neighborhood is still shrouded in mystery. The evidence leaves us with one undeniable truth. The universe continues to send us enigmas that stretch the limits of our science and remind us of both our fragility and our curiosity in the face of the unknown.